calculating what we call the theoretical yield. How much aspirin should you have been able to make based on the quantities that you use? In the PowerPoint presentation, you see that you have certain statistics about each of the chemicals that you used in the process to make your aspirin. So you had salicylic acid. This is its molecular formula. You had acetic anhydride, which is your molecular formula. The phosphoric acid was just a catalyst. So really, the catalyst just helps the process go faster by minimizing the amount of activation energy necessary for a chemical reaction by creating alternative mechanism steps. So the phosphoric acid was a catalyst. And if you remember from the notes, this guy, the phosphoric acid, is what attacks this molecule, which allows it to break these bonds in order to attack this part of your salicylic acid. Now, there are certain facts. We know the molar mass of the salicylic acid. We know the molar mass of the acetic anhydride. Those are the two key reactants, okay, that we use to make this final product, which is acetylsalicylic acid. Now, we know, based on the balanced chemical equation that was given in the lab, that 1 mole of salicylic acid can produce 1 mole worth of acetylsalicylic. And just remember that a mole represents a certain number of particles, 6.02 times 10 to the 23rd molecules in this case. So that meant 1 mole of salicylic acid molecules will produce 1 mole of acetylsalicylic acid. Now, the technical name for salicylic acid, just in case you wanted to know that, if you recall that you had the benzene ring with a carboxylic acid group on it, when that happens, we have a nickname for that combination. It's called benzoic acid. But on the benzoic acid, there was an OH group in the second position relative to where the carboxylic acid is. So in the naming process, because we had a benzene ring, as we discussed in class, what we're saying is on the top here was the carboxylic acid functional group, and the OH group was in the second position relative to this one. We also told you in class we call that an ortho position. Okay, so it was ortho. Another way of doing that, we can number the ring 1, 2, and say this OH group, called a hydroxy group, was on the second position on the benzene ring with the carboxylic acid functional group on the top. So that's where the technical name comes from. We know its molar mass is 138.12 grams per mole. So let's say we know that let's say hypothetically we start out with 2 grams of your salicylic acid. Okay? We know that what does 2 grams mean in moles? To figure that out, we would take the mass and divide it by the factor, right? 1 mole of salicylic acid is equivalent to 138.12 grams per mole. So now we converted the quantity that we started out with to moles. But we also know that 1 mole of aspirin can be created from 1 mole of particles of salicylic acid. So now what we did is we converted our answer in the first part of this mathematical equation to moles of aspirin. Now we know how many moles of aspirin we have from 2 grams of salicylic. We can figure out how many grams that is because we know that 180.17 grams of aspirin can be created from 1 mole of when you have 1 mole of aspirin. And what we just calculated is the mass of aspirin, theoretically, that we should get from 2 grams of salicylic acid. But we would also want to figure out, that's only if the salicylic acid was what we call the limiting reagent. We'd also want to prove how much would we get based on the acetic anhydride that we used. Based on the density that is given to you in the lab for the acetic anhydride and the volume of the acetic anhydride you used, I want you to use the same calculation to figure out theoretically how much aspirin you should get. The one that gives you the smallest amount of grams of the aspirin is what we call the limiting reagent. So if you did the calculation for based on the salicylic acid mass and the acetic anhydride, the answer that gives you the smallest quantity of grams of aspirin is what we call the limiting reagent and the correct theoretical mass of aspirin, because that single reactant is really controlling the final quantity. So this all works from this balanced chemical equation here that says 1 mole of salicylic acid creates 1 mole of aspirin. 1 mole of acetic anhydride creates 1 mole of aspirin. So again, if we based it on the 2 grams of salicylic acid, technically we would get 2.6 grams of aspirin, right? But you would also want to do it to prove that either the salicylic acid or the acetic anhydride is the limiting reagent that's going to control the theoretical yield that we're going to get. So that's where you're getting this information that you would fill into this chart here. So you got mass of salicylic acid. That's the mass that you weighed out initially. I gave you the molecular formula of salicylic acid. Based on your grams that you use, figure out how many moles of salicylic acid you used. You're going to fill in the molar mass, which technically I gave you in the lab, so you could just fill that in. Then you also know the density of the acetic anhydride. You knew the volume that we used. We didn't use 5 milliliters. We used less because we mini-scaled. So you want to put that number, you want to change that number in your lab. And you want to determine what is the mass of acetic anhydride. There's an error here. This should be acetic anhydride that you used, right? You want to put that in here. I give you the formula mass of acetic anhydride. You can figure out how many moles you used. And then determine which one of the reactants, the salicylic acid or the acetic anhydride, is the limiting reagent, and place that chemical name right here. Now what you want to place into your data table is what is the mass of the actual aspirin you synthesized. You're going to figure that out on the following lab day because the aspirin is drying right now. And once completely dried, you're going to remass it. You knew the mass of the medicine container you put it in. You now take the difference between the mass of the medicine container and the sample you have minus the mass of the container, and you could get how many grams you have in that container. Okay? Based on that, you can figure out how many moles of aspirin you have because I'm giving you the formula for the aspirin. Figure out its molar mass. Moles is equal to the grams that you have divided by the molar mass, which is how much 1 mole of that chemical would weigh in grams. And you figure out how many moles of aspirin you synthesized. Well, there is what we call the theoretical yield, what you should have gotten, and what did you get. So based on the limiting reagent, you figured out what your theoretical yield of aspirin should be. So you take the mass of your aspirin that you synthesized divided by the theoretical yield. So you're going to take this number right here and you're going to divide it by this number right there times 100 would give you your experimental yield of aspirin. Okay? So what you're trying to figure out is how much aspirin did you get, and you're going to put that in here if you multiply it by 100. Now, with the aspirin sample, what we're going to do is we're going to do different tests. We're going to get its melting point and compare it to the melting point it should be. We're going to do a thin layer chromatography analysis to see what is inside our sample. Is it just pure aspirin? We suspect there should be some salicylic acid also still left in there because the reaction was at equilibrium. Eventually, we'll do a visible spectroscopy analysis. But if we had some more high-tech equipment like an infrared spectrophotometer, we could actually scan the samples and see what types of bonds are present. By scanning the different infrared photons at the sample, we could get bond vibration, bond stretches that would tell us what kind of bonds are present. And we would get a graph that looks like this, which says at this wave number, which is related to wavelength, we have an indication of an OH group. So that would be your OH group on a salicylic acid. This peak right here would basically be telling us that we have an acid functional group, which both the aspirin and the salicylic acid would show that peak. But the aspirin would not show this OH peak because the aspirin wouldn't have that. So if you did a comparison, okay, there is the missing peak for the OH, but there is the peak. This peak right here is this combination, this functional group combination. Right? That's what that peak would indicate, which is called an ester functional group. And that peak there would still be your acid functional group that's present in your aspirin, and also the salicylic acid. So those would match. So you can use this like a fingerprint. Now this peak here is also an indication of an ester functional group. You notice that the guy on the top doesn't have that. The graph on the top doesn't have that. So you would get something like this, right, on a real infrared spectrophotometer. And then based on these peaks that you have, you would match them up to the type of functional groups or bonds that would be present in a molecule that would give this absorption of infrared photons. Problem with this reaction, you can have side reactions. Like if we let it react at a very high temperature, we could get what we call polymerization, because we know that an ester functional group can react with an OH functional group, and you would actually dehydrate water, and you would get a bond between these two functional groups and create esters. This molecule has a whole bunch of ester functional groups. So we would create some sort of what we call polyester if we heated the molecule too long. And if you see oil in your product, okay, that typically would indicate that this happened. We represent this polymer. Typically, polymers are represented by this type of structure where we show the repetitive unit throughout the molecule that keeps repeating. So this is the repetitive unit, and N represents how many times does that show up in the molecule. And that's all dependent on the size of the polymer. Okay, so I will see you tomorrow, and we will continue our research on our aspirin sample.